In this lecture we will go through some second order filter examples. We begin by the same circuit that we considered in our previous lecture, but this time we will be collecting output from somewhere else. Okay, so the circuit was a second order RLC, series RLC circuit. Okay, and in the previous example we collected the output as the voltage of the resistor. This time we're collecting it from this pair of terminals, okay, considering this as a single component in a sense, the capacitor and inductor combination. This is the input voltage. The impedances are SL 1 over SC, and here we have R, the resistance. Okay, let's compute the transfer function from this input to that output, and then try to figure out qualitatively certain properties of the gain response. Okay, so the transfer function V out of S divided by V in of S is simply the equivalent impedance made by the inductor and capacitor connected in parallel divided by the overall impedance seen by the input voltage. Okay, so what we have therefore is SL plus 1 over SC. Okay, so that's this impedance Z divided by Z plus R. So that's the overall impedance seen by the input. SL plus 1 over SC plus R. Okay, and this can be simplified into following: H of S equals S squared plus 1 over LC over S squared plus R over LS plus 1 over LC. Okay, in the previous example, which turned out to be a bandpass filter, we had in the numerator R over L times S. Okay, so this time what we have in the numerator is S squared plus 1 over LC. Okay, now let's try to figure out the gain characteristics for that transfer function. For that, let us introduce the notation omega 0 as 1 over square root of LC. Okay, then we have the following: H j omega. Okay, so that equals, okay, now omega 0 is 1 over square root of LC, so this is omega 0 square, and this is also omega 0 square, and what we have as H omega is omega 0 square minus omega square, so that's our numerator, and in the denominator we have omega 0 square minus omega square, so that's the real part, and the imaginary part is J R over L omega. Okay, so at the frequency omega equals omega 0, what we have is numerator is 0, therefore the transfer function is 0, therefore its gain is also 0. So what we have is H omega 0 equals 0. Okay, so at the frequency omega equals omega 0, the gain produces 0. So that means for frequencies that are close to omega 0, the gain is something quite small. Okay, let's also talk about the extreme cases when omega equals tiny and when omega equals very large. So at Hj, let's say 0, okay, so this is what happens at very low frequencies. Let's say what we have is plug in omega equals 0, or when omega is very small. When omega is very small, then the numerator is dominated by omega 0 square, that constant. Likewise, the denominator is dominated by the constant omega 0 square, because this term and that term, they vanish, or they can be ignored compared to omega 0. And what we have is omega 0 square over omega 0 square for omega very small, and then that produces something around 1. Okay. Also, at frequencies that are very large, let's say omega close to infinity, this time the numerator is dominated by minus omega square term, okay, because it's very large, therefore larger than that constant omega 0 square. Likewise, the denominator is dominated by the same term, minus omega square. So what we have is, at very large frequencies, hg omega approximately equals minus omega square over minus omega square, and that produces again 1. Okay, so roughly, therefore, we can claim that the gain should more or less look like hg omega versus omega, the following. This is 0 at low frequencies, we're at 1, and at high frequencies, again, we're close to 1, and somewhere in the middle, at omega equals omega 0, we hit the bottom, okay? So this is the reverse bump, okay, or the dip. Therefore, clearly, what we have is the type of this filter is such that this band, okay, the frequencies around omega 0 is not, in a sense, those signals are not let appear at the output side, okay, so because they're attenuated. And for frequencies that are far from omega 0, that is for low enough frequencies and for high enough frequencies, the signals are passed to the other side, and we see them, we collect them from the output. Therefore, this is a bandstop filter characteristics, okay, so this produces bandstop filter, okay, and it would be a nice exercise to obtain the phase, again qualitatively, roughly, obtain the phase characteristics of that transfer function. Okay, now let's move on to our second example. Okay, this time the topology of our circuit is as follows. Okay. From this port, we supply the input as voltage, and from the second port, we collect it again as voltage. Okay, so this is V in, and this is our output voltage, LCR. Okay, so let's figure out the transfer function, and then once we have the transfer function, we can study its phase and gain characteristics. Okay, so we are asked to do the following: find the transfer function h of s, b, sketch the gain and phase plots, and the last part is do the numerical part, compute bandwidth, quality factor, and cutoff frequencies for the parameter values. R equals 1 kilo ohms, C equals 1 microfarad, and the inductance given as 10 millihenries. Okay. Solution. Let's obtain the transfer function, which can easily be derived by a simple voltage division. Okay, so H of S equals. Okay, let's call the equivalent impedance of this parallel connection Z. Then the transfer function can easily be computed through voltage division, which is Z over the overall impedance or the input impedance seen by the left port, okay, which is R plus Z. Now Z is Z is SL and 1 over SC, those impedances connected in parallel. So let me put it here. H of S equals, so we have the parallel connection, which is SL times 1 over SC, SL plus 1 over SC. Okay, so that term in the numerator is the parallel connection for this L and C in S domain. Okay, divided by R plus Z. R plus Z, so that's SL 1 over SC, SL plus 1 over SC. And that simplified produces 1 over RC S, and then the denominator reads S squared plus 1 over RCS plus 1 over LC. Okay, therefore this is clearly a bandpass filter. Now what's H J omega? Okay, so let's write down H omega, and by looking at it we can qualitatively or roughly comment on the gain and phase characteristics. H omega reads J1 over RC omega over minus omega square plus J1 over RC omega, okay, plus 1 over LC. Okay, so let's figure out what happens at low frequencies, at high frequencies, and also at the center frequency. Omega equals omega 0. Okay, omega 0 is 1 over square root of LC. This is our center frequency. Okay, when omega is around 0, okay, the denominator is dominated by 1 over LC, okay, and the numerator is J 1 over RC omega. We have one term in the numerator, and then since that term is multiplied by omega, at omega close to 0, what we have is J 1 over RC omega divided by 1 over LC. Okay, since omega is tiny, that produces as gain something very small. So that means when omega is around 0, okay, the gain is also around 0. How about the phase? H G omega. Again, for omega small, what we have is 1 over LC as the denominator, so that's what dominates the denominator, the phase of which is 0. Okay, so therefore at low frequencies the phase of H omega equals the phase of the numerator, and the phase of numerator at all frequencies is pi over 2 radians or 90 degrees. Therefore at low frequencies H omega is around 90 degrees. Okay, let's figure out the other end, the other tail. At high frequencies, this time this term dominates the denominator, and Omega is also high, but this is a second order term, omega squared. Therefore, the magnitude of omega squared is much larger than the magnitude of omega when omega is large. That means the gain is again very insignificant at high frequencies. Okay. So H j omega tends to 0. How about the phase? Okay. The phase of numerator, as we said, is always 90 degrees. And at high frequencies, this is the dominating term. It's negative, therefore its phase is 180 degrees. So the overall phase is 90 minus 180, so that produces minus 90 degrees. Okay. Okay. And let's also figure out gain and phase at the center frequency. This is something that we already did. But let's plug in omega equals, okay, let's plug in omega equals omega 0, okay. And then this term is minus omega 0 square. This and that, they cancel. And what we have is j 1 over RC omega divided by the same thing. Therefore, at omega equals omega 0, the gain of our filter exactly equals 1. And how about phase? Since H omega itself is 1, okay, not only its gain but also itself is 1, therefore it's positive real. That means its phase is 0 at the center frequency. H j omega equals 0 degrees. Okay, so with that rough analysis, we can obtain approximate plots for the phase and gain functions of our transfer function. Okay, so we have therefore this as the gain. We start at 0, we make a peak at omega 0, and then again for high frequencies we tend to 0. Okay, so this is our gain plot, and the maximum value which is attained at the center frequency equals 1. What else? This is the phase omega H omega. Okay. Now what we do is at low frequencies the phase is around 90 degrees, and at very high frequencies it's minus 90 degrees, and at the center frequency we cross the plus minus border. Okay, so that means the phase will look like this. This is minus 90 degrees. This is where we start 90 degrees, and when we cross the 0 degree point, the frequency is omega 0. It equals center frequency. Okay, now let's talk about the numerical part, part C. So h of s, the transfer function, fits into our bandpass prototype, and our notation for bandpass prototype was ks over s squared plus 2 alpha omega 0 s plus omega 0 squared. Okay, for which we derived earlier that bandwidth equals 2 alpha omega 0, and that equals, okay, that equals here 1 over RC. And for given R and C values, that equals 1 over 10 to the 3 times 10 to the minus 6, and that's 1000 radians per second. So that's the bandwidth of our bandpass filter. And the center frequency omega 0 squared equals 1 over LC, and that equals 1 over 10 to the minus 2, 10 to the minus 6, and that produces 10 to the 8. Hence, omega 0 is 10,000 radians per second. Okay. And 2 alpha omega 0 equals 1 over RC, which is the bandwidth, 1000. And so this equals 1000, and omega 0 is 10,000, from which we can figure out alpha. Okay, 2 alpha omega 0 equals the bandwidth, which is 1000. That produces alpha equals 1 over 20, 0.05. Okay. Now, how about the quality factor? Okay, quality factor is, by definition, the ratio of the center frequency to bandwidth. So for our filter, omega 0 over b reads 10,000 over 1,000, which is 10. Therefore, our filter is a narrow band filter. And as for the cutoff frequencies, C1, 2 equals omega 0 1 plus alpha square plus minus alpha. Okay, so that equals 10,000, which is our omega 0 value. 1 plus 1 over 20 is square, so 1 plus 1 over 400 plus minus 1 over 20. Okay, well, this can be approximated as 1, because 1 over 400 is quite tiny. Hence, the cutoff frequencies are at approximately right, 10,000 plus minus 500 radians per second. Radians per second, and omega C2, the larger cutoff frequency, is at 10,500 radians per second. Okay. Now let's move on to our next example. Okay, now the circuit, or our filter, contains an operation amplifier, therefore it's called an active filter. This is the topology of our circuit. V2. R2, C2. R4, R3, and here we have C1 and R1. And this is where we apply the input. And this node is where we collect the output, denoted by V1 and V2 respectively. Now for this circuit, we are asked to first find the transfer function. Okay, V2 of S over V1 of S. So this is our output and this is our input. Let's call our transfer function H of S, which we usually do. And then once we have H of S, we are asked to determine what type of filter does this circuit make. Okay, so that's B. And in the last part, we have to design our filter according to the following constraints. Choose the parameter values. Okay, Ri, the resistances no less than 1 kilo ohms, and the capacitances no larger than 10 microfarad, such that filter has cutoff frequencies at 100 radians per second and 2500 radians per second. Okay. Furthermore, the passband gain H omega max is wanted to equal 10. Okay. So let's start our solution. Now we're going to obtain the transfer function. So suppose that we transformed the circuit in S domain. Okay, so the resistances, we don't touch them. The capacitors are now represented by their impedances, 1 over S C1 and 1 over S C2. Okay, furthermore, we assume that the circuit, the op-amp is in linear region. So to obtain the ratio V2 to V1, let's obtain first the sub-ratios and then we can just take their product to obtain the ratio that we're looking for, which is our transfer function. So what I mean by that is the following. So we have in S domain V plus over V minus equals. Okay, so V plus is this node voltage. This is V out. And here, since there is no current escaping into the op-amp, because we're working with the ideal op-amp model, this voltage, this V plus can easily be obtained through voltage division. Okay, 1 over SC1 divided by the overall impedance seen by V1, which is R1 plus 1 over SC1. So V plus over V1 therefore equals 1 over SC1S divided by 1 over C1S plus R1. Okay, and that's 1 over R1 C1 S plus 1 over R1 C1. So that's our V plus over V1. And then from V plus we go to V minus, which is easy. V minus over V plus equals, the op-amp is in linear region, therefore these two node voltages must be equal to one another. Okay, hence we have the ratio 1. Then comes V0 over V minus. This is the output voltage of the op-amp, okay, not of the filter. And then to figure out V minus in terms of V out or vice versa, again we can make use of a voltage division here. So V out over V minus, okay, equals R4 plus R3 over R4. Okay, This is V out. Here we have V minus, and the whole voltage is V out. And then finally, let's figure out the ratio of V2 to V out, which again we computed through a simple voltage division. Okay, and finally, we have V2 over V out, okay, which equals V2 over V out, which equals R2 over the overall impedance seen by this node voltage V out. So that produces R2 over 1 over C2S, excuse me. Okay, 1 over C2S plus R2, and that simplified reads S over S plus 1 over R2 C2. Okay, now we have all the intermediate ratios, which when written in a product form will produce the ratio of V2 to V1. So let's do that and obtain our transfer function. Now we write V2 over V1 equals V2 over V out times V out over V minus times V minus over V plus times V plus over V1. Okay. All these sub-ratios are here. We just computed them, and clearly that product produces V2 over V1. Hence, V2 over V1, or in other words, our transfer function equals, after the simplification, R3 plus R4 over R4 times 1 over R1 C1. That's multiplying S over S squared plus 1 over R1 C1 plus 1 over R2 C2S plus the product of those two terms, R1 C1 R2 C2. Now that denominator polynomial can be written as S plus 1 over R1 C1 times S plus 1 over R2 C2. Therefore, the roots or the poles of the transfer function are at minus 1 over R1 C1 and minus 1 over R2 C2. Okay, so this prototype we immediately recognize belongs to the bandpass filter, where we have used the following notation: Ks over S squared plus 2 alpha omega 0 S plus omega 0 square. So that means this thing here is our K. This thing here, the coefficient of the first order term, equals to alpha omega 0. And finally, this 0th order term is our omega 0 square. Okay, so the answer to part B therefore is this circuit has bandpass filter characteristics. Okay, now let's move on to the last part, the design part. We were given the cutoff frequencies from which we can compute the center frequency omega 0, because we know that the center frequency appears as the geometric mean of two cutoff cutoff frequencies. Okay, so omega 0 equals omega C1, omega C2, and then you take the square root. So that means omega 0 equals square root of 100 times 2500. That produces 500. Radians per second. Okay, so that's our center frequency. Now, using this piece of information, let's also figure out the alpha, the damping factor. Omega C12 equals, okay, remember the cutoff frequency expressions in terms of omega 0 and alpha. Cutoff frequencies were at 1 plus alpha square plus minus alpha times the center frequency, okay, from which directly we obtained in one of our earlier lectures that omega 0 equals the geometric mean of two cutoff frequencies. Okay, now we know the cutoff frequencies, we have just figured out omega 0, therefore we should be able to obtain alpha. Let's take the smaller cutoff frequency, which was at 100. 100 equals center frequency 500 times 1 plus alpha square. Since it's a smaller cutoff frequency, this should be minus, okay, and that's our equation from which we obtain alpha. Okay, so that means 1 plus alpha squared minus alpha should equal 100 over 500, or 1 over 5. And that produces alpha equals 2.4. That's our damping factor. Okay. Now, remember that it's already here, actually. The denominator polynomial equals s plus 1 over r1 c1 times s plus 1 over r2 c2. In other words, the poles of our transfer function are at minus 1 over r1 c1 and minus 1 over r2 c2. Now, this is the prototype for which we now have omega 0 and alpha. We can express the roots in terms of omega 0 and alpha, okay? And then that will give us something, a constraint on 1 over r1 c1 and 1 over r2 c2, from which we can start our design. Okay. Now the poles of the transfer function are the roots of the denominator polynomial, or the solution of the characteristic equation, which produces the following roots. S12 equals minus omega 0 alpha plus minus alpha square minus 1. Okay, so omega 0 and alpha we now know, therefore we know the roots. We also know that the roots are at minus 1 over r1 c1 and minus 1 over r2 c2. So that should equal minus 1 over r1 c1 and minus 1 over r2 c2. Okay, so S12 using the numerical values that we obtained for omega 0 and alpha equals minus 500 times 2.4 plus minus over 25. Okay, and that produces S12 equals minus 2 2290 approximately, and minus 110. Okay, therefore this pair must equal minus 1 over R1C1 and minus 1 over R2C2. So R1C1 suppose equals 1 over 2290, and R2C2 equals 1 over the other root, or the magnitude of the other root. Okay, and then let's pick the resistance values, and then once those resistance values are picked, capacitance values immediately follows. Okay, so we were told to choose the resistance values not smaller than 1 kilo ohm, so therefore let us choose them both at 10 kilo ohms. Okay, so R1 and R2 are now chosen, and from which we can obtain C1 and C2. Okay, so that produces C1 equals 44 nanofarad, and C2 equals about 900 nanofarad. Okay, and let's also talk about the constraint regarding the maximum value of the gain function Hg omega max, which we know is achieved at Hg omega 0, okay, omega equals omega 0, and which we know in terms of our prototype parameters equals k over 2 alpha omega 0. Okay, so that means k over 2 times alpha was 2.4, omega 0 was 500, okay, and that equals, which is given, equals 10. Okay, so because we want the maximum value of the gain function to equal 10, and from that equation we see that k has to be 24,000. Okay, k equals 24,000. And now let's write k in terms of our circuit parameters. So what we have is 24,000 equals the k in terms of our circuit parameters, which was R3 plus R4 over R4 times R1 C1. Okay. Now R1 and C1, or R1 C1, is now known, and from this equation, therefore, we obtain the ratio of R3 to R4. Okay. So this is what? 2290. Okay. Therefore, we have R3 plus R4 over R4 equals 24,000 divided by 2290, and that approximately equals 10. Okay, which means the ratio of R3 to R4 should be what? 9. Okay, and we can therefore choose any resistance values with ratio 9, and they should be over 1 kilo ohms. So let's choose R3 as 90 kilo ohms and R4 as 10 kilo ohms. Okay, and these values should satisfy the design constraints.